Hello everyone, thank you to all of you who are coming here to watch my video today on logistic growth. In Calculus 8b, the exponential growth model, this is also something we did in BC last section, was derived from the fact that the rate of change of a variable is directly proportional to the value of y. Using the differential equation dy dx equals ky and its general solution y equals ce to the kt, you may have noticed the exponential growth is unlimited. However, when describing a population, there often exists an upper limit L past which growth cannot occur. This upper limit L is called the carrying capacity. It represents the maximum population Y that can be sustained as time t increases. A model that depicts this type of growth is called a logistic differential equation and looks like what we see here, where K and L are positive constants. The logistic differential equation of that form results in a solution that looks like this. So if you recognize this is a logistic differential equation, which automatically can be put into this equation form. Let's take a look at a couple examples from some old AP questions. Number one, the differential equation of a logistic growth model given by dy dt has a solution of y. Find a solution to the logistic growth model for the differential equation with y of 0 equal to 1. All right, so first of all, we're going to want this to look like this. Okay? Now, in order to do that, what we're going to do is we're going to factor out, we want this to be 1 here. So we're going to factor out a 10 from both sides. So it's going to be 2y times 10 times 1 minus y over 10, which would be 20y times 1 minus y over 10. Okay, so therefore, we can be confident that k is 20 and L is 10. Okay, so now to find the b value, we can use the point 0, 1. All right, so now we're going to use this equation and put all the numbers in that we know. So we're going to have 1 equals L, which is 10, over 1 plus B, E to the negative 20, and then T right now would be 0. So E to the 0 is just 1. So now we're left with 10 over 1 plus B. So 1 plus B equals 10, so B equals 9. So using these three numbers right here, I can come up with the fact that our answer for this problem must be B. Number 2, the logistic number of phytoplankton specimens in a laboratory tank at time t is increasing according to the logistic growth model. Which of these following statements could be true? All right, let's just go one at a time. The first one, this one could not be true. Why? Because that right there is positive. That would mean it's not growth. That would actually mean that it's decay. If you look back at our equation here, it's supposed to be negative for it to be growth. So it can't be A. B, well, this isn't even logistic growth. This is exponential growth. So it's not B. C, if C was true, that would imply that this is concave up the whole time. But we know logistics aren't going to be concave up or down the whole time. They're going to be a little bit of both. So it's not C, which means by default it has to be D. But let's just make sure it is D. Before we did the separation of variables here, and both sides, the model would probably look something like this. dp dt equals 0.035 times P times 1780 minus P, which is a proper logistic growth model differential equation. So our answer here is D. Question 3. The spread of an infectious disease to workers on a large floor of an office building is modeled by logistic equation P of T, where T is number of days and P represents the number of infected people. The graph is shown. What is the number of infected people when the rate at which the disease is spreading the greatest? Okay, well, a couple things to notice here. We're looking for when the slope is the greatest. That's going to be right about here. Okay, the answer looks like it's about 400, but how can I actually prove it to be 400? Okay, so the answer is 400, but how can I be for sure? So it's important, a little important note here is that it's going to be the fastest when the curve has reached a point of inflection. Okay, when does a curve reach a point of inflection for logistic growth? That happens when it reaches half of its carrying capacity. So, what is the carrying capacity? In this case, it's 800. So half of that would be 400. So that's why the answer would be C. Besides the fact that it just looks like it from the picture. Question 4. The rate at which natural gas is being extracted from an underground reserve at time t satisfies the differential equation dg dt, where g is measured in thousands of cubic feet and t in weeks. Clearly, that's a logistic growth differential equation. Okay? For it value of g is the extractant rate the fastest. So again, this goes back to the last problem. It's increasing the fastest when it reaches half of its logistic growth capacity. So the carrying capacity here is 64. So simply half of that, it's increasing the fastest at 32. That is when it is half the capacity, and that is when there would be an inflection point in the graph. All right, a free response question. Here we go. A conservation organization releases 30 panthers into a preserve. After 3 years, there are 50 panthers in the preserve. All right, so that gives us 2 points. The first point is 0, 30. The second point is 3, 50. The preserve has a carrying capacity of 150, so that means L is 150. The growth rate of the panther population is given by dp dt, which is clearly logistic growth, which has a solution given by P. All right, so number 1 says find L. Well, L is the carrying capacity. We've already got that. It's 150 panthers. All right, question 2 says find B. We'll use this and this to find B. So 30 equals 150, 1 plus B e to the 0, which is just 1. So it's 150 equals over 1 plus B. So 30 plus 30b equals 150. 30b equals 120. B equals 4. And now we'll use our next point to find K. All right, so we got 50 equals 150 over 1 plus our newly found B, which is 4, e to the negative 3k. So solving this, we can do this a couple different ways. I'm going to go ahead and just multiply both sides by that whole denominator here. All right, and then subtracting 50 and dividing by 200. We get there. All right, now we're going to convert that into logarithmic form. So negative 3k equals ln of 1/2. So then k equals ln of 1/2 over negative 3. So a couple different things we can do with to simplify this. We can write this as ln 1 minus ln 2 over negative 3. ln 1 is 0, so it's negative ln 2 over negative 3, which is just ln 2 over 3, or 1/3 ln 2. So k equals 1/3 ln 2. So the next question says, take everything we just found and write that as a model for the population. All right, so that's just going to be P of T equals 150 over 1 plus B, which is 4, e to the K, which is 1/3 ln 2 T. Question E says, use that model to predict the population after 12 years. All right, we're simply going to put 12 in for t. So we get 150 over 1 plus 4e to the, so negative 1/3 times 12 is negative 4 ln 2. And we can use our calculator to help us with that. It's going to be approximately 120 panthers. Remember, for actual animals here, we're going to round around to the nearest whole number if needed. So 120 panthers would be our approximate guess. All right, and finally here, for the limit of the model as t approaches infinity. So the limit as t approaches infinity of our model here. All right, so if we put infinity in there, we get 150 over 1 plus 4 e to the all that stuff times infinity. So it's just e to the negative infinity. That's all. So it's 150 over 1 plus 4 over e to the infinity. This is going to be infinity. So 4 over infinity would be 0. So it's 150 over 1, which is 150. Which makes sense because that is the carrying capacity. All right, that will do it for our lesson today on logistic growth models and differential equations. Thanks as always for checking in, and we'll see you again soon.